Hi, my name is Seung-won Park. I'm an undergraduate researcher from MindsLab and feel honored to present our paper Cotatron at this year's Interspeech. One of the standard approach for voice conversion is to obtain speaker-independent features from speech and then combine with target speaker's information for resynthesis. However, the previous methods cannot utilize the transcription and still lack the quality for real-world applications. In our work, we show that pre-trained multi-speaker TTS can be exploited to disentangle the speaker information from the speech. We named our method as Cotatron since it is mostly based on the famous TTS architecture, Tacotron. The figure on the left side shows the Kotatron architecture. By teacher forcing the TTS decoder with null spectrogram, we can obtain the alignment between the speech and its transcription. Then, the Kotatron features are obtained with matrix multiplication between the text embedding and the alignment, which are both speaker independent. By training a decoder to reconstruct the speech from Kotatron features and speaker information, we got the state-of-the-art results on voice conversion between 108 speakers from VCTK dataset, which is shown in the table on the right side. We also show that Kotatron generalizes to unseen speakers by showing the any-to-many conversion. The audio samples and source code for our paper is available on GitHub, and please refer to our paper and full video if you're interested. Thanks for watching, and I'll be more than happy to answer the questions. Hi, my name is Seung-won Park. I'm an undergraduate researcher from MindsLab, and today I'll talk about our novel speech encoder named Cotatron. Let's get started by talking about the definition of voice conversion task. The task of voice conversion is to change speaker identity of speech without changing its content. Thus, the typical voice conversion architecture looks like the figure shown here. The content encoder is designed to remove the speaker identity from speech to obtain the speaker-independent linguistic features. Then, the linguistic features are combined with the target speaker's information to synthesize the converted speech. Our main contribution is on disentangling the speaker identity from speech by incorporating the transcription of the speech. According to a literature called OWC, perfect speaker disentanglement and reconstruction will lead to an ideal conversion. In our work, we aim to construct an ideal speaker disentanglement module and train voice conversion system with only reconstruction loss. The overall architecture of our voice conversion system is shown here. In this figure, the yellow blocks represent the input or output, the light blue blocks represent the trainable modules, and the green blocks represent the intermediate representations. First, Kotatron encodes speaker-independent linguistic features from speech and its transcription, which we call as a Kotatron features. Next, the optional residual encoder encodes the speaker-independent prosodic features from speech. Finally, the decoder combines the speaker-independent features and target speaker's information to synthesize the converted speech. Let me explain the modules one by one. First, I'll explain the Kotatron module, which is the most important part of our paper. Before talking about Cotatron, let's have a look at Tacotron 2, which is one of the most widely used TTS model. The Tacotron 2 is trained to generate a single frame of maum spectrogram from the previous frame, which is also known as the teacher forcing method. After the training, the Tacotron 2 becomes able to obtain the alignment between the maum spectrogram and its transcription. This is why we can build the Tacotron 2 as an unsupervised alignment learner, since we do not need to provide supervision on the alignment. This test audio alignment motivated us to propose the Cotatron module for speaker disentanglement. If we train the Tacotron 2 with multi-speaker dataset by adding the speaker encoding module, then the output of the text encoder will be naturally speaker independent. Furthermore, the text audio alignment does not contain any information that is relevant to the speaker identity, except the rhythm of the speech. Therefore, we can obtain the speaker-independent linguistic features with a matrix multiplication between the alignment and the text encoder output, which is shown in the equation number 2. From now, we call these features as the Kotatron features. Please note that the length of the Kotatron features is identical to that of the source maum spectrogram. Next, I'll talk about the residual encoder, which encodes the extra features from the maum spectrogram for better voice conversion. What prompted us to build the residual encoder was to realize that the Kotatron features alone isn't enough for the best conversion quality. Sometimes the decoder failed to correctly reconstruct the source spectrogram with Kotatron features. since the intonation of the speech may vary within the speech of the same text with an identical rhythm. As shown in the figures on the left side, the intonation shown in the reconstructed spectrogram differs from the source spectrogram. To fill the gap of information, we designed a residual encoder to propagate the residual information that can aid the voice conversion quality. The residual encoder successfully helped the decoder to accurately reconstruct the source spectrogram. However, we observed that too much information is being encoded in residual information, which is speaker dependent and harms the conversion quality. To make sure that the residual features are also speaker independent, we made very narrow information bottleneck. After passing the layers of two-dimensional CNN, it is projected to a single dimension and then smoothed with hand window. The temporal smoothing with hand window prevented the residual encoder from learning to encode too much information with fluctuation, as shown on the left. To provide speaker embedding, a learnable embedding lookup table is used. The lookup table could be possibly replaced with CNN-based encoder, however. Nearly identical result was observed. One of the interesting future work regarding this would be using a speaker verification network to enable the system to generalize to unseen target speakers, which will be few-shot targeted voice conversion. The last module is the voice conversion decoder. The VC decoder is constructed with a stack of residual blocks with a conditional batch norm layer to inject the speaker embedding. We have tried the other conditioning methods inspired from HyperNet or StyleGAN too, but we empirically observed that most of them led to worse results. Please note that the VC decoder is only trained to reconstruct the spectrum with representation from the identical speaker. So now I finished explaining the modules consisting our voice conversion system. Let me introduce the training objectives. Step 1. Only the Kotatron is trained with typical Kotatron 2 loss, which will eventually lead the module to correctly infer the text-audio alignment. An auxiliary speaker classification loss is added to encourage the training of the speaker encoder of the Cotatron. Step 2. Other parts of including Kotatron is trained with reconstruction loss. During this step, Kotatron is set to evaluation mode. Let us revisit the training objectives with the figure shown before. On the left side, the speaker encoder for Kotatron and an auxiliary multi-layer perceptron classifier is trained with speaker classification loss, while the autoregressive TTS decoder is trained with original Kotatron 2 loss. On the right side, all trainable modules excluding the Kotatron is trained with reconstruction loss. We use VCTK and ReviTTS dataset for training and evaluating our voice conversion system. The VCTK dataset, which is commonly used as a benchmark dataset for voice conversion, is consisted of 108 speakers. We manually split them into train validation and test set with respect to their transcription to prevent the text overlap between the sets. The ReviTTS dataset is incorporated to stabilize Kotatron training, since the Kotatron could not be trained from scratch by only using the VCTK dataset. To assess the performance of our system, two subjective metrics and two objective metrics are measured. We measured the MOS and DMOS with human evaluators from Amazon MTurk to assess the naturalness of and the speaker similarity of the converted speech. And for the objective metrics, the speaker classification accuracy is measured by training and using the CNN-based speaker classifier. Furthermore, to measure the content consistency between the source and the converted speech, the voice activity detection module is used to measure the voicing decision error. The results of many-to-many voice conversion is shown in this table. We compared our method with Flow, which is the only literature that showed the performance on voice conversion between all speakers from VCTK dataset. In terms of both MOS and DMOS, our method outperformed the previous state-of-the-art model with a significant margin. These results show that the Kotatron features are effective for providing disentangled representation for voice conversion system. It should be noted, however, that SCA, the speaker classification accuracy, which is the objective metric for speaker similarity, contradicts the DMOS, which is the corresponding subjective metric. We also show the any-to-many voice conversion results, since the Kotatron is able to generalize to speakers that are unseen during training. We used the speakers from Liberty test cleaning as an unseen speakers for this experiment. Furthermore, we have tested whether the input transcription for our system can be replaced with ASR without affecting the performance. Our results show that the conversion from unseen speakers are also possible, which we will demonstrate with the audio samples. Also, using the ASR for transcription did not affect the performance at all. This shows that the fully automated conversion pipeline without performance degradation is possible. From now on, let's listen to the audio samples that shows the effectiveness of our method. In this slide, a conversion results between speakers of VCTK dataset is shown. The first row shows the source speech for the conversion.
Our task is to complete the picture.
The second row shows the example of speech from target speaker.
But he just carried on anyway.
The third row shows the conversion results with previous method below.
Our task is to complete the picture.
And the last row shows the conversion result with our Kotatron-based system.
Our task is to complete the picture.
Here we can realize that not only the naturalness, but also the speaker similarity of converted speech is better than the previous method. This slide shows a conversion result from unseen speaker to demonstrate the possibility of any-to-many conversion. The first is the source speech from Liberty test clean split.
What did it mean?
The second is an example speech from target speaker.
First and foremost, the game is entirely different.
The last one is the conversion result.
What did it mean?
Next, we show that our system is robust against word errors of ASR, since most of them originate from the words that have similar pronunciation. The source speech with a correct transcription is shown in the first row.
Shareholders will be asked to approve a new replacement scheme.
The second is an example speech from target speaker.
I've got to provide for my family.
The converted speech with a wrong transcription from ASR is shown in the last row.
Shareholders will be asked to approve the new replacement scheme.
Here we can observe that even the errors from ASR exist. The conversion result has consistent content with the source speech. And this is a famous speech of Charlie Chaplin from the old film, The Great Dictator.
We want to live by each other's happiness, not by each other's misery.
Let's convert it to a speaker from VCTK dataset.
We are just glad to be alive.
The result looks like this.
We want to live by each other's happiness, not by each other's misery.
This example clearly shows the possibility of any-to-many conversion, which can significantly extend the possible range of real-world applications. So we have explored the application of Kotatron on voice conversion. There are a few other potential applications of Kotatron. First, while training the Kotatron, we observed that the reconstructed mode spectrum is sometimes clearer than the source. This is perhaps because the text was given as an additional information. Through this observation, we might think of text-informed speech enhancement with Kotatron. Another potential application of Kotatron is a lip motion synthesis. Most of the lip motion synthesis models, like the one shown here, relies on the audio features extracted from ASR model. We think that the Kotatron features will be better at this, since Kotatron can receive text as an input to provide more rich linguistic features. Finally, to accommodate the comparison with future works, we show the degree of disentanglement from our method. The CNN-based speaker classifier is trained on top of each speech features, and the classification accuracy is measured with test dataset. The accuracy with only Kotatron features was 35%. This is much lower than the result with mode spectrogram, however. It is quite far away from this perfect disentanglement. These speaker classification results does not fit well with the performances that our system have shown, and we leave at the future work to discuss such discrepancy. Our main takeaways are as follows. The multi-speaker TTS can be exploited to disentangle speaker identity from speech. The speaker encoder was added on the Kotatron 2 decoder to make Kotatron generalize to unseen speakers, which makes any-to-many voice conversion possible. Also, the residual encoder was proposed for better conversion quality. We hope that the Kotatron will open a new path towards multimodal approaches for traditional speech processing tasks, including the speech enhancement, limb motion synthesis, and possibly the emotion recognition. Our work is available on GitHub, where the PyTorch code and pre-trained models are open. You can also listen to more audio samples on our GitHub page. Thanks for watching, and I hope our work to inspire future works that can benefit from speaker disentanglement. Thank you.